All right. Ready for another day of physics. Because physics is fun. All right, so last time we started chapter 19 we started? Which has all to do with electric potential and electric field. And so lab yesterday we used electric potential to find electric field. And let's see, we got all the way to equipotential lines. We got all the way to 19.4, I believe. And we were going to go ahead and get started on capacitors and dielectrics today. So that's where we will begin. I wonder where Scott is. He's not here yet. Everybody, this is Sam. Sam is one of our podcast students, and this week she's not at work in the morning, so she's going to join us for class today. Are you changing schedules again next week? So
yeah, we just have to do 2 weeks of option this semester.
Okay. So we'll see her for today, and then she'll be gone again, and then we'll see her again later. Sam was a student here a few years ago, and volleyball player in physics and everything. So now you're doing med school, pre-med. That's right. Cool. All right. This is my son Packer. You may remember him. And this is not my son Phil, who is looking into engineering as a career. And then we have Scott, who's just taking classes for fun because the military's paying for it. So he's like, cool. Free college. Hey, I'm not saying it's a bad thing. He took a bullet for me, so he literally took a bullet and has the Purple Heart. He deserves to go to school for free on the tax dollars. It's fine with me. Never got to take the bullet in the butt.
Yeah, no, I'm really sad about that.
All right, so we're going to talk about capacitors today, which a capacitor is a device that takes advantage of this phenomenon that we've been studying, the electric field, to accomplish many tasks, but primarily among them is to store charge. So the simplest form of a capacitor is just two metal plates. And here is a little diagram of one where you have one metal plate, one other metal plate separated by a gap of whatever, and you can connect it to something that will charge up the plates, but the idea is to charge them with opposite types of charge. So here, if we connect it to a battery, one plate to the positive side of the battery, one plate to the negative side of the battery, what the battery is going to do is it's going to drive charge from one plate to the other. It's going to drive electrons from one plate to the other. And it will drive them from this side to this side so that the plate that is connected to the positive side of the battery ends up losing electrons and becoming positively charged, and the side that's connected to the negative side of the battery will become negatively charged. Now, what happens when you have a negative or a positively charged material and a negatively charged material facing each other? They are attracted to each other. We're going to prevent them from being attracted. But let's go back one section and take a look at equipotential lines between two plates. Right? This is what happens is you can essentially decide which plate you're going to call your 0 volt plate, and the other plate will have some voltage different from that because of the difference in charge. And you will get variable voltages in between with these equipotential lines here. But then the field lines will go perpendicular to those lines, just like we learned yesterday in lab. And you get an electric field in between the plates here. And this electric field, essentially you can connect this thing to the battery and then disconnect it. And the electric field will actually hold those charges in place so that they don't go back through the battery. And once you've disconnected the battery, you've actually stored charge in this capacitor. So it's kind of like, you know, a poor man's battery. You don't have to have any chemistry, you don't have to have any enclosed structure, you don't have to have any acids or lead or anything else. Just a very simple way to store charge. The downside to it is that it doesn't store very much charge compared to chemical batteries for the most part. Also, to store more charge, you essentially just have to make the dumb thing bigger. The upside is that a capacitor can release its charge extremely quickly compared to batteries, because there's almost no resistance in a capacitor, whereas batteries do have resistance. And the other upside is that you do have this electric field as well. It's not just a storage of charge, but it's a storage of energy inside of an electric field. So as you're building up this electric field, you're building up more and more energy. There is a limit to it, because eventually you'll make so much electric field that something will happen. What happens when you build up a lot of electric field through like air? You get lightning striking, right? And if lightning strikes from one side of this capacitor to the other, it will lose its charge. Because what's going to happen is the electrons will jump across from one side to the other, and then it will neutralize the capacitor. So it won't be charged anymore, and you won't be storing the electricity. So that's another downside to capacitors, is that they do have this limit to them. Batteries also have a limit that is determined by the chemistry of the battery, materials of the battery essentially. This one is determined by more geometry in this case, but we'll figure out a way to fix that. We'll figure out a way to lessen this electric field without lessening the amount of charge. We'll learn about that soon, in a minute here. So the capacitor has actually many shapes and forms. Here's another type of capacitor that is just a variation on this one. This one we call the parallel plate capacitor. This one down here we call a rolled capacitor or a coil capacitor, where you take parallel plates and you roll them up, and you put something in between them to prevent them from touching. And it turns out that putting that material in between them to prevent them from touching, like paper, it's usually some kind of paper impregnated with oil or plastic or something, it turns out that that actually makes the capacitor more capable of holding charge. In other words, you can put more charge on it without the charge jumping from one side to the other. And so that was a very fortuitous kind of discovery, it turns out, and it has been used to great advantage, many, many times. Well, we need to now put together some kind of a equation that's going to tell us how much charge we can store on these capacitors, and that how much charge we can store, we're going to call its capacitance. So what is it that determines this? Well, we've already said that there's going to be a limit to how much charge we can stuff on here. The more charge we put on one side or the other, the less it's going to want more charge to be put on. So you put the first charge on, the first electron over there, and it's happy as can be. But another electron, if you try to put another electron on there, it's starting to get crowded. You know, and then another and another and another and another. The more electrons you put on, the more they resist another electron putting on, because electrons repel each other, right? And the same thing on the positive side. The more electrons you take off, the harder it is to take electrons off, right? Because electrons are attracted to positive and they want to stay there. And so it gets harder and harder to charge the capacitor the more and more you charge it. Eventually it just doesn't want to be charged anymore. And so one of the things that's going to affect the capacitance is going to be the size. The actual size of the plates. If you have bigger plates, you're going to have more room for electrons to kind of hang out there without getting repelled by each other. So the size of the plates matters. The area, in other words, of the metal plates matters. The closeness of the metal plates, it turns out, really matters. But it's difficult to maybe imagine why it matters so much. If the plates are further apart, it turns out that the plates don't necessarily want to hold as much charge. Now, why would that be? Imagine the plates as having some kind of a thickness. Now let's take a look at this. Let's draw this out a little bit here. I'm going to draw it on my screen, which is awkward for me, but it makes it easier for people watching this later. Let's start with that. What do I have to do? Start with video. There we go. So let's imagine that these plates have a thickness to them, which of course they do. That's not a very good straight line. And we start putting electrons on one plate by taking from the other plate. So this one ends up having less electrons than normal, and this one ends up having more electrons than normal. What's going to happen to the electrons on this plate and the electrons on this plate once we bring these plates closer together, or close together? Remember, electrons repel each other. So if you have an excess of electrons over here, you have more electrons than normal. What's going to happen to the electrons over here? They're going to get pushed to this side. It's going to polarize, right? So that you have most of your electrons that are left over here on the left side, and you're going to have bare positive charges over here, right? Which also means that the electrons over here are going to get attracted to this side, and these are going to be positive out here, right? And what that means is that it's going to actually be pretty easy as these get closer together to bring more charges around, because these electrons over here will want to come over here because they're going to see positive on this end, right? And these electrons are going to be more and more attracted over here. So it has to do with how the electrons orient themselves in each individual plate. So the closer the plates get together, the more charge you can put on them. However, the closer they get together, the more likely they are to spark across as well. So there's kind of a give and take relationship there. But the closeness is an inverse thing. So the closer they get, the smaller the distance gets, the bigger the capacitance gets. And the bigger the plates get, the bigger the capacitance gets. So we have a relationship that looks like this. Capacitance is proportional to distance between the plates as an inverse. So we put that in the... Whoa. What happened? Drop. There we go. Capacitance is inversely proportional to the distance between the plates, it turns out. And it's directly proportional to the area of the plates. Goodness. Why does it keep doing that? Directly proportional to the area of the plates, it turns out. So if you want to increase it, you increase the area of the plates and decrease the distance. If you want to decrease your capacitance, decrease your area, or increase the distance, or both. And that will decrease, it turns out. So that's a start, but it turns out that area divided by distance is not going to give you a unit that says charge. It's not going to tell you how much charge you can put on this thing. It's going to give you, area divided by distance is just distance. So you're going to have some kind of constant in here to make this an equation. And that was done by our friend Coulomb. No. Was it? I can't remember who did it. But somebody did it. And they were able to determine that the capacitance of a parallel plate capacitor does have this area divided by distance thing in it, but it has this constant in it that we call the permittivity of free space, which essentially tells us how much charge wants to jump across free space or a vacuum. It's called epsilon naught. That's the name of that symbol, epsilon 0 or epsilon naught. And the value of that constant is measured to be 8.85 times 10 to the minus 12, and its units are farads per meter, which ends up giving us farads, and farads are a unit that look like this, Coulomb squared per Newton meter. Is that right? It's if we take out the per meters here, then it's farads. It's Coulomb squared per Newton times meter, something like that. But anyway, it gives you the correct units that we want in the end. Just like other constants we've encountered in physics, just give us the correct units. But that's how you essentially calculate the capacitance of a parallel plate capacitor. The capacitance in general is defined as the number of, or the amount of charge per volt. So it's kind of like charge per potential, right? But to actually calculate it for a capacitor, a parallel plate capacitor, it ends up being epsilon naught times the area over the distance between the plates. So here's a very simple example where we calculate the capacitance of a capacitor where they give us the area, they give us the voltage applied to it. They give us the area and they give us the distance of separation. And then they Then they ask how much charge is going to be stored if we put a particular voltage across it. So that's what the other equation comes in. So just calculating the capacitance, it's just area divided by distance times that constant. Very simple calculation. You get 8.85 times 10 to the minus 9 farads. So 8.85 nanofarads, which is a very common capacitance. 8.85, something in the nanofarads or even the picofarads. So nano is 10 to the minus 9, pico is 10 to the minus 12, femto is 10 to the minus 15, right? So picofarads, nanofarads, microfarads, very common kinds of types of capacitances, because capacitance, big capacitors are difficult to make. A 1 farad capacitor can be very, very big, but we've discovered ways to make them small. We'll learn about that in a minute. But they can be very big. I've seen a 1 farad capacitor the size of a Volkswagen Beetle, for example. Just a huge stack of parallel plates in a big bath of oil. So yeah, 1 farad capacitors can be extremely huge. But once you've calculated that capacitance, then you can use it in the definition of capacitance, which is Q equals C times V, or C equals Q over V. Charge over voltage, right? And you can rearrange that equation to calculate the charge or to calculate the voltage if you have the other two things. Since we already calculated the capacitance, and the capacitance is the maximum amount of capacitance. That tells you the biggest capacitance it could hold. And since capacitance is charge per voltage, it's not necessarily how much charge it could hold. It tells you how much charge it can hold per voltage that you apply to the capacitor. So if you apply a certain voltage, then you can calculate the amount of charge on that particular capacitor using that capacitance, which is exactly what they do here. We've already got the capacitance from part A. They tell us the voltage we want to apply to that particular capacitor, and the amount of charge that will move from one side to the other on that capacitor will be equal to C times V. So you do 8.85 times 10 to the minus 9 farads, which we got from part A, multiplied by the 3,000 volts that they give us, and we get 26.6 microcoulombs of charge passing from one side to the other to create that charge storage. Now, what is the electric field that you're going to see or you're going to be able to detect inside that capacitor? Well, electric field is voltage divided by distance. And the voltage that you apply to the capacitor will be the total voltage across that capacitor. That's essentially the same thing, right? And so electric field is voltage divided by distance. The distance is the distance across the capacitor. You go ahead and put those in, and you get 9 times 10 to the 6 volts per meter for your electric field. They say that it's a negative because they're saying they're giving it a direction from one side to the other. Yeah. But once you have this kind of electric field, 9 million volts per meter, that's easily enough electric field to cause lightning to strike. So this capacitor is not going to be able to handle that amount of voltage. It's going to break down if it's just a capacitor with air in it. So what we do to prevent that capacitor from breaking down, to prevent it from the charge from jumping from one side to the other, we put something in between that lowers that electric field, that allows you to have that kind of voltage, but it changes the dynamics because you're no longer in a vacuum. It changes what's going on because you're no longer in a vacuum. It actually lowers the electric field between the plates is what it does. It cuts it down. So how do you do that? Well, this is how you do it. Here's your parallel plate capacitor. You got your positive side and your negative side. And you put in a material in between that's some kind of insulator. Now remember that in insulators, your charges don't move around from one end to the other of the insulator, but they can move in the sense that they can polarize. Remember that insulators could polarize. They don't necessarily polarize as much as a metal does, but they can polarize. Water polarizes, for example. Water is an insulator. It is not a conductor. Water is only a conductor when it's contaminated with things like salt and sugar and dirt and junk like that. But pure water is an insulator. But its molecules will polarize because they will rotate so that their positive end faces negative charges and their negative end faces negative charges. or sorry, faces positive charge. Positive faces negative, negative faces positive. So this is what it would look like if you put a material where the molecules are allowed to rotate or kind of shift a little bit so that they're attracted to opposite charges. You get the negative sides of each of these molecules pointing towards the positive side of the capacitor, and the positive sides pointing towards the negative side. And what happens inside the material is that you get an electric field that actually opposes the electric field of the capacitor. The electric field of the capacitor is pointing from the positive side to the negative side, but the electric field inside this material is going from the positive side, which is the right side, to the negative side, to the left side. So this one's going from right to left, and the other one is going from left to right. And those things will start to cancel each other out. The electric field of the material inside will be exactly opposite. It won't be as strong, but it will be exactly opposite the electric field inside the capacitor. So then you've lowered the electric field inside the capacitor, and lightning may not strike at that point, depending on the material you put in and how much charge is there. But what this does is it allows you to have more capacitance for a material for a capacitor once you put the material inside of it. We call these materials dielectrics. This effect that the material undergoes here is called a dielectric effect.
That's the brown unit with the pattern on the top, right?
What's that?
Dielectric is the brown unit when the capacitor blows up.
Okay, so yeah, in like a capacitor on a column, like on a power pole, if it explodes, this brown stuff goes everywhere. That is actually oil, and the oil is a dielectric oil, and it has two purposes. It acts as a dielectric, so it increases the capacitance of the capacitor, but it also acts as a coolant, because capacitors in AC environments often get hot. So it's always a good idea to have something that can pull away that heat, and that's also why the capacitors have heat sink vanes on the outside to dissipate that heat into the air. So you see these power poles with these kind of buckets on them. Sometimes those buckets have capacitors in them. Not always, but sometimes. Sometimes they have other things in them we'll learn about later, inductors. But essentially what happens, you put something in between two plates of a capacitor that is non-metallic, you will get an increased capacitance there. And what it does in the equation is it changes the constant out in front. Instead of just epsilon naught out in front, you get this other constant that multiplies it, called the dielectric constant. And every different material has its own dielectric constant, and it will change the capacitance, usually increasing it. Well, always increasing it if it's a dielectric material. And the dielectric constants of different materials are here. So the dielectric constant in a vacuum is 1. So in other words, if you're in a vacuum, it doesn't change anything at all. If you just have nothing between the capacitors, it just behaves like it normally would. But if you have air in there, air is slightly better than vacuum. It increases the capacitance by a tiny little bit, way out here at 0.00059, right? But bakelite, which is, remember those old antique phones that are made of that black plasticky material? That's bakelite. And bakelite has a dielectric constant of 4.9, which is pretty good. You have fused quartz, which is used often in essentially glass, used in capacitors all the time, 3.78. Neoprene rubber, very good at 6.7. Pyrex glass, 5.6, much better than fused quartz. Then you have water. Water turns out to be a fairly good capacitor. Strontium titanate, another very, very, very good one. Right? Love that, 233. Water has to be pure. Can't have any contaminants in it. But there's one that's even better than all these other ones that will even increase. So you put in strontium titanate, and you get a really good capacitor. It's 200 times better than it normally would be. But 200 times better than a nanofarad, 10 to the minus 9 nanos. That's not that much better. There are materials that will give you hundreds of thousands and even millions or billions times, like a dielectric constant in the millions. And this material is called aerogel. And we've seen that before, right? We saw that last semester. So aerogel is the least dense material on the planet, and it can be made of just about anything plasticky, anything that's got a polymer kind of feel to it. Because aerogel is made by taking plastic materials and um, and kind of infusing them with air bubbles. And so this is what it looks like. It looks kind of like, I don't know, what does it look like?
Solid smoke.
Yeah, it looks like smoke that's a solid material, right? And this stuff is extremely low density. Like this piece right here could be a block 10 centimeters by 10. It could be a foot cube block, this big, and weigh less than a gram, easily. It wouldn't be hard at all. But it could also support something like this. Like this is supporting a granite block, 2.5 kilogram brick. It's supported by a piece of aerogel that has 2 grams of mass to it. So this thing is, this block, I can't really see it that well, but there's this little piece of aerogel underneath it. And it's being supported, this thing is 1,000 times more massive than the thing supporting it. And it doesn't cause it any harm at all. It's extremely strong. Another one of the extreme characteristics of aerogel, particular aerogels, is that they can be infused with different materials. And those materials that normally could not be used as a dielectric material can be used when they're infused into aerogel. So aerogel is a very useful material. You can form it into many different things like fabrics, which make it very nice for, it's got all kinds of cool properties. So. Aerogel, here's a block of aerogel being supported by a dandelion. That's how little mass there is in that block of aerogel. A dandelion isn't even squished by it. So there are, and the lightest forms of aerogel will actually float around in this room because they have less, or not less density, but they're about the same density as air. So you can get a block of aerogel this big, release it in this room, and it will just float around, and eventually it'll fall to the ground if there's not much air current. But if there's any air current at all, it'll just kind of float around again like a balloon full of air. It's a solid material that's that impressive. So anyway, aerogel capacitors can be 1 farad and be the size of your pinky. They can be very, very tiny. You can't put a lot of volts across them generally because they just don't have enough area to support a high voltage. So I think the highest voltage 1 farad capacitor that I've seen that's an aerogel capacitor that's very small is maybe 10 volts. But it can still hold a lot of charge with that 10 volts. You can really pack it in. Anyway, once you know the dielectric constant of a particular material, then you can calculate a new capacitance for a capacitor that uses that material in between its plates. Now, remember that these equations are for parallel plate capacitors. They don't really work very well for other different types of capacitors, and there are many different kinds. You can make a capacitor between any 2 conductors that can hold, that you can charge up. So it can be a wire and a tube, it can be a can and a ball, it can be anything. Capacitance is built up all the time. It can be a car and the road, You get capacitances built up between your car and the road all the time. A cloud and the earth. That's a capacitor. Right? All right, so here they show some pictures of what happens when molecules polarize and atoms polarize. For an atom, when you have an unpolarized atom, you have this uniform distribution of charge where the nucleus is somewhere there in the middle, and the electrons kind of hang out outside in a grouping or a pattern that is very uniform. It's spread out in a spherical kind of uniform pattern. But when you bring in some kind of external charge or an external field, electric field, then electrons tend to kind of go to one side of the atom. They tend to go hang out away from, electrons tend not to hang out away from the negative side of the field and are attracted towards the positive side of the field. So that's what happens with polarization. It's not necessarily a rotation, although it can be more like a rotation with molecules. But with atoms, it's generally more just a shifting of electrons. So this side looks more positive and this side looks more negative, or seems more negative. Same thing with, it's the same thing with water. You can get rotation, but you also get this shifting. Let's go look at the capacitor lab on PHYS website here. See if it's any good. I don't remember. I haven't seen it in a while. Oh. So here we have our capacitor. Let's go ahead and show our capacitance in the meter here. It's a measuring device. This can just go away. Let's get rid of that. Okay. So anyway, if we change our separation here, which we should be able to do, here we go. Get them closer, the capacitance goes up. Get them further apart, capacitance goes down. Right? Make our area of our plates bigger, capacitance goes up or down. And let's detect our electric field. If we get our plates closer together, what happens to our electric field? Let's see. Why don't I see it? Oh, because I don't have, there we go. So now I'm giving it some voltage. So there's my electric field is going from the positive plate to the negative plate, and if I bring them further apart, the electric field decreases. Closer, electric field increases. Right? If I increase the plate size, it doesn't change the electric field, it just changes how much charge I can store. So it doesn't change the electric field. Anyway, I suppose that's interesting. Put a dielectric in. Let's see what it looks like now. Electric field detector. So now our electric field, without the dielectric inside, is pretty strong, right? But then if we put our dielectric in now, what happens to the electric field? I need to fix it here. I need to make this less. And this here. So what we've done is we've added an electric field from the dielectric to the electric field from the plate, and we start to get a different thing going on in there. So notice that the number of charges increases too, right? The number of charges on each plate increases because we can store more charge for the same amount of voltage, because we've decreased essentially the electric field in here, so we can put more charge on and increase that electric field again. So it's kind of nice. There we go.
And that electric basically keeps it from, like, do capacitors have like a trickle, like between the plates? Where it's
Yes.
passing a little bit?
They do. In real life, there's always some leakage current, they call it, as current leaks through the dielectric material. Because no material is perfect insulator. It does have a leakage current, and if you're doing really high precision electronics, very, very sensitive electronics, you need to know those details, and you can look them up or you can measure them. But nothing that we do in this class will ever worry about leakage currents. Anyway. Somewhat interesting, I suppose. So here's a nice little aside, I suppose, call it. You've probably heard of diffusion, if you've taken a biology class, of things going through a membrane in a cell, for example, salt ions moving in and out. What do they call that when? Osmosis or something like that. These things happen because of a dielectric and an electric field. When you have a membrane and you have different things on either side of the membrane, it behaves like a capacitor. The membrane behaves like a dielectric, and the materials on either side of it behave like the plates of a capacitor. And there will be different charges on either side because of the different materials. So inside of a cell and outside of a cell actually have different charges to them because they have different ionic concentrations. Usually it's ions of salt. So whenever you put salt into water, if you remember your chemistry, the salt breaks apart into its two ions. The water, the electric field of water molecules just does that to salt. And so the salt breaks into two different ions, and one of them is positively charged, one of them is negatively charged. And inside of a cell, there's a different concentration of those ions. There's a different mixture of those ions than outside of a cell. And so it's like having a different charge on either side of a membrane that behaves like a dielectric. And that different charge allows other charges, other salt ions to pass through. So it maintains a balance. So if you have an imbalance, it allows the ions to move through the membrane and you create a balance. Without that, we'd have all kinds of difficulties maintaining salt balance in our body. And we have to have that because the salt ions do a lot of the carrying of things around in our body. They allow things to move through this diffusion process. So, but it is at its heart, it's a capacitor. At the very heart of it, it is electric field, electric potential, charges, attraction, repulsion. And so physics really can be applied to many, many things the closer you look at them. And since we're able to look more closely at what's going on in biological systems these days with new imaging techniques and analysis techniques, physicists have gotten a lot more involved in biology in the past 30 years or so, 30 or 40 years, to describe things and discover new things. Okay, so now we're going to move away from the theoretical and move on to the practical. Capacitors are used in circuits, plain and simple. We use them for different things in circuit design. Some very important things, for example, your cell phone could never work without capacitors. One of the main things that your cell phone does is it picks up a signal that is sent out into the air in every direction. It even gets out into space and into the water and into the buildings and everything else. And this signal, there's millions of them, millions of different ones, and your cell phone can pick one of them out of the mess that is the electromagnetic, quagmire in the universe. There's just so many different signals that your phone might pick up, and it picks one and picks it up, right? Imagine that you're in a hurricane and there's a butterfly in the hurricane and you can hear the butterfly flapping its wings. That's what your cell phone does. That's what it can do, okay? So it's impressive what it does. And it could never do it without capacitors. Without capacitors, it could never pick that one little butterfly's flapping wings out of a hurricane. So it's essential. It's an essential component. Very simple thing, but essential to what to the things that we do every day. So we're going to talk about capacitors in electrical circuits. A very simple electrical circuit here. We've got a battery connected to 3 capacitors, one after the other. So the one side of one capacitor is connected to the next side of another capacitor, the next side of it is connected to the next side of another capacitor, and so on. This is what we call capacitors connected in series. They're one right after the other in series. There's no connections branching off anywhere. They're just one right after the other and then back into the circuit. When you create a capacitor like this, it is the equivalent of creating one big capacitor that has a distance between the two plates equal to the sum of the distances here. So it's like having one capacitor with a bigger distance. And if you have a bigger distance with a capacitor, what's that going to do to your capacitance?
Increase.
Remember that the D is an inverse, right? So capacitance is proportional to A over D. So if D gets bigger, C gets smaller, right? So this actually decreases the capacitance if you put them in series like this. And sometimes there's a reason for that. There's definitely purposes to putting capacitors in series, but it will decrease your capacitance. And mathematically, what we do to figure that out is we calculate voltages across the capacitors. We add them together, voltage 1 plus voltage 2 plus voltage 3, to get the total voltage, which would be the voltage across the battery. And using our definition of capacitance, that would mean that the Q over the total capacitance, which we call capacitance S for capacitance in series, would equal to Q over capacitance 1, Q over capacitance 2, Q over capacitance 3, because those are the definitions for voltage according to the capacitance definition. And then, since they're all the same charge, because they will all be the same charge. If you put a charge of 10 coulombs here, you're going to get negative 10 here. And then because you have negative 10 here, you're going to have 10 here. And because you have 10 here, you'll have negative 10 here. So the charges will all be the same on all the capacitors. So since they're all the same on all the capacitors, we can just divide that out, and we end up with an equation that looks like this. That 1 over the total capacitance of the capacitors in series is equal 1 over the capacitance 1 plus 1 over capacitance 2 plus 1 over capacitance 3, and so on and so forth. So you get this inverse relationship for calculating the total capacitance of capacitors that are in series. So what's the trick to this? The trick is to calculate each one of these 1 over capacitances separately, add them together, get a total, and then take the inverse of that, and that will tell you your capacitance. Right? So here is the example. We're going to put 3 capacitors in series, 1, 5, and 8 microfarads. And we want to know what the total capacitance would be. And it should be less than the smallest capacitor in this series. So the smallest one is 1. This should end up being less than 1 microfarad. Let's see if it's true. So we take 1 over 1 microfarad plus 1 over 5 microfarads plus 1 over 8 microfarads. And the answer to that is 1.325 over microfarads, because microfarads is still in the denominator. And to get the actual capacitance, we need to invert this. We need to flip it over. So 1 over 1.325 microfarads. And that ends up being 0.755 microfarads, which is less than 1 microfarad. So that makes sense. Your total is less than the capacitors to begin with, less than the smallest one, and you're good to go. Here they do the same problem, but they do it using common denominators, and you can do that. I find it easier to just plug it in my calculator, but it's up to you. But what happens if we do these in parallel? What does it mean to be in parallel? Well, if you connect each one of these capacitors to the positive side of the battery on one side of the capacitor, and then each one of the capacitors on the other side to the negative side of the battery, you get a setup that looks like this, where you have one wire connecting all 3 of one side and one wire connecting all 3 of the other side. And when they're like this, it's like they're in parallel, because we have 3 parallel branches of our circuit here, right? 3 of them lined up next to each other, look like parallel lines. And that is the equivalent of having a capacitor where you just take the area of each capacitor and add it to the area of the next one and add it to the area of the next one. So it's like having a capacitor with a huge area equal to the area of all 3. And what happens if you increase the area of a capacitor? If you increase the cross-sectional area and you give it more room for charge to be, it'll have more capacitance, right? So it increases the capacitance, and this is easy. If you have capacitors in parallel, you just add up the capacitances to get the total capacitance. Simple as that. Just add them up. Capacitor 1 plus capacitor 2 plus capacitor 3 and so on equals the total capacitance of capacitors in parallel. So for the same example, if you have a capacitor 1 microfarad, a capacitor 2, 5 microfarads, capacitor 8 microfarads, you get a total capacitance, if they're in parallel, of 14 microfarads. Much simpler than if they're in series. So now what we're going to ask you to do is to do a little bit of, this is more kind of organizing your thoughts and making sure that you see things properly. But we're going to give you things like this little circuit of capacitors, and ask you to calculate the total capacitance, where some of the capacitors are in series and some of them are in parallel. And the way that we do this is we first look for capacitors that are in series. So these two capacitors are in series for sure. And what we do is we calculate their capacitance as if they were one capacitor in series, and draw a new circuit and replace those two capacitors in series with a new capacitor with the calculation that we just made for the new capacitor. And then after we've finished combining all of our capacitors in series, then we look for capacitors that are in parallel. Capacitors that are in parallel, remember, this is important. If they're in parallel, they must be connected to each other on both sides, with nothing in between. If they're in series, they must be connected one after the other with nothing in between. There can be no branches in between and nothing else in between. But if they're in parallel, they must be connected on each side to each other with nothing in between, but you can have branches in between, but you can't have any other components. So if you had a capacitor over here instead of this branch, these would not be in parallel, even if they look like they're in parallel. Okay? And then you combine capacitors that are in parallel by just adding them together to get a total capacitance. So let's do this here. We're actually going to do this very one. I'm going to copy that image. I'm going to go to my thing here and do this on the screen. All right. So let's clear our board here. Let's see, I thought I could paste something on this, but now that I'm looking at it, I don't think I can. Doesn't look like it. That's okay. We'll just draw it on. So we've got these. Come on. Why won't it let me draw? Well, that's just nice. It won't let me draw. Why is it doing this to me? There we go. Now it lets me draw. Okay. So anyway, we have this circuit that looks like this. We've got a capacitor here, and then come around, we have a capacitor on the other side. And I'm going to actually make this a little more complicated, just because I want to be that way. I'm going to put a capacitor out here and a capacitor here. Connect it there. Why not? And I'll put one right here. We just love it. Okay. So the trick here is to figure out which capacitors are in series. Because if they're in series, then we can combine them to make a new capacitor. And then hopefully we'll get rid of all the ones in series, which is the hardest thing to do first. And then anything left will either just be by itself or in parallel. And parallel, that stuff's easy to deal with. So we start off by figuring out which ones are in series. So are there any capacitors that are in series in this drawing? I'm going to go ahead and label these. This will be 1, 2, 3, 4, 5, and 6. So what capacitors are definitely in series up here?
1 and 2.
1 and 2 are in series because they're one after the other and there's nothing no branching off in between, no other thing in between. So 1 and 2 are in series.
5 and 6.
1 and 2. And you say 5 and 6 are in series,
Yeah.
connected to each other, nothing in between. Any more? It's tempting to say maybe that, I don't know, somebody might be tempted to say 3 and 4 are in series. You know, they're connected one after the other. But there's a branch in between. Not allowed, right? Or even 4 and 5 and 6 all in series. Tempting, but there's a branch in between. So it's not true. So what we want to do is we want to create a new capacitor to take the place of this one, and a new capacitor to take the place of this one, and then replace them and make a new circuit, right? So the capacitor that we're going to replace here, we'll call this one capacitor A. So capacitor A will replace 1 and 2. Dang it! Why does it keep doing that? And 5 and 6 will be capacitor B. And according to our equation, according to our understanding of this, 1 over capacitor A, which is what's going to be the result of these added together, has to equal 1 over capacitor 1, right? 1 over capacitance 1 plus 1 over capacitance 2. So what is capacitor B going to look like? What's that? So 1 over capacitance B, remember you have to do that part as well, because that'll tell you that you have to switch it at the end. 1 over capacitance B equals 1 over capacitance 5 plus 1 over capacitance 6. And then you'll put in the numbers here, calculate it, you'll get a number, and then you'll flip it over to get capacitance A. You'll do the same thing for capacitance B. And then we're going to replace them. So our new, and I would recommend you draw this out, otherwise it gets confusing. You're going to put a new capacitor that's going to replace 1 and 2, so just one capacitor in that place. Call that one capacitance A now. And then we still have capacitance 3 over here, so we'll put it back to where it was. Right? We still have capacitance 4, it's still in its place. But over here where 5 and 6 were, which is between here and here essentially, we have a new capacitance that we call capacitance B. Right? And remember that capacitance, these capacitance 5 and 6 were connected to capacitance 4, and they were also connected actually here on this side of capacitance 3. So essentially there's a kind of a short circuit there. So there's a connector there, they're connected to 4, they're connected to this side of 3, and this one was also connected on the other side to 3 and to these two capacitors. So I'm just making sure all my connections are correct. So this capacitor was connected between 3 and this one. It was connected between 3 and 4. Right there. It was also connected to 4 right here. Okay, so all the connections are correct. Now, we have a new circuit. Are there any capacitors in here that are connected in series? No. You might be tempted to say that there's a capacitance here, B and 4 might be in series, but there's a branch in between them. 4 and 3 might be in series, but there's a branch in between them, right? So they're not. So now we're looking for capacitors that are in parallel. Do we have any capacitors that are in parallel? 3 and B are connected in parallel, right? So if 3 and B are connected in parallel, then we just add those two together to make a new capacitor, right? The problem with that is my circuit has a short circuit here, so that new capacitor is going to be connected to both sides of capacitor 4. So that's going to be a little bit of a problem. That's okay. It's just an error in creating a circuit without thinking about it. Are 3 and A connected in parallel?
Not
No, because of this short circuit, right? So then you're done, because there's nothing else connected in parallel after that. Add those two together, make a new one, and you're good to go. But that's the kind of thing that you have to do these problems. And that's why I wanted to show that to you really quick. Goodness. All right. So something that has a circuit that has capacitors in series is simplified down to two capacitors in parallel, because the series ones got combined. Then the two in parallel get simplified down to a single capacitor. And in circuits, even very complex circuits, you can simplify the entire circuit of capacitors down to a single capacitance. And the entire circuit simplified down to a single capacitance, you can understand a lot about the circuit in general that you may not understand when you're looking at the circuit with all of its particulars in place. All right. So here they actually do the math of this. They add the first two capacitors together, in the 1 over fashion here for capacitors in series. And then once they get that number, they invert it and get the capacitance of the series capacitance. Replace that in the diagram there. So they replace the two capacitors over here with one capacitor, which is CS, this one right here. And then since CS and C3 are now in parallel, they can just add them together to get the total capacitance. So they do that, get the total capacitance, and they're done. In this particular example, you don't have anything in series, so you go directly to parallel, right? Nothing is in series. So you go directly to parallel, just add these two together to get a single capacitor here at 12.5 microfarads, and then you have something in series. So then you add them together in series, 1 over the 12.5 plus 1 over the 0.3 microfarads, and you get a number, invert it, and that will tell you the total capacitance. So it's not always in the order of series to parallel, but it sometimes is. If you have two that are definitely in parallel to begin with, it's easy to combine them, so you might as well do it first. Here's an interesting example. We have these capacitors over here on the left side and this one over here, and it might be really tempting to say that these ones are in parallel with this one. They are not. Okay? These two capacitors are not in parallel with this one. If you combine these capacitors to make a single capacitor, then that single capacitor will be in parallel with this one. But don't try to do it the other way because it will mess up your math. Okay? So first, combine these because they're in series, then that will make a single capacitor over here that is definitely in parallel with this one. Then you can add them together. Now here's one that might confuse you again, but you'll be happy to hear it's a simple one. You have two capacitors here. Are they in parallel or not? Remember, the definition of parallel is that each side is connected to the other side. So the two sides are connected to the other two sides with nothing in between. Is it true here? Absolutely. You can go from this one to this one without anything in between, and from this one to this one without anything in between. Perfectly valid. Right? Even though there are branches off here, that's fine. There's no components in between. Series is the only thing that cares about branches. Parallel doesn't care about branches. So, anyway, that is our first practical lesson in capacitors. What time is it? And I believe this is our last section. Yep. So how do we calculate the amount of energy stored in a capacitor, and why would we want energy in a capacitor? We would want energy stored in a capacitor so that we can bring somebody back to life. right? That's what a defibrillator does. A defibrillator is a capacitor, and it's got, depending on the defibrillator, some defibrillators are meant to be standalone units, so they have a battery that that essentially powers up the capacitor, that gives energy to the capacitor, and then you discharge the capacitor through the heart of the victim, right? Why does that do anything for the victim? Because it gives them a really quick, very fast jolt of energy at just the right energy level to make the heart start beating again. It just gives it the impulse that the heart is used to feeling, right? Why don't we use just the battery in the defibrillator to do that? Doesn't discharge fast enough. A heartbeat, you remember the EKG signal that has the little boom, boom, boom thing, the little spikes in it, right? That is a time frame. The width of those spikes is a time frame. And if you don't get the width correct, if you don't get the time frame correct, your heart doesn't recognize the pulse. The muscle will not react to it if it's a longer pulse. So it has to be a very quick pulse. It has to be just the right time length. So you have to use a capacitor to get that kind of time length. And so defibrillators used to be huge units. Now they're much smaller. Why?
Because now we have some.
Now we have capacitors that are smaller, can still hold that amount of energy because of these new capacitors using things like aerogels, right? It used to be a defibrillator was carried around on a cart and sometimes plugged into a wall, like in a hospital defibrillator, right? And if it was carried around in a cart, they would have them in ambulances, but they'd carry it out in a cart or a suitcase because it had a car battery and it had a big old capacitor in it that was just humongous. They were not convenient. Now you can carry it around almost in your back pocket. They're small, so small, right? So defibrillators have come a long way just because of the materials that we use to make the capacitors and the batteries. Both things have improved greatly. Capacitors are used in many other things as well, though. For different reasons. In older cameras that had flashes, like this camera here, the flash bulb was lit off by a capacitor. You'd actually hear it charging up. When you turned it on, you'd hear this little whining thing. And what that was is it was a battery charging a capacitor so that you could light off the flash. Nowadays we just use fast-acting LEDs, but they still use capacitors, just not very big ones. So anyway, how do you calculate the amount of energy stored in a capacitor? Well, remember that we learned just recently that potential energy is equal to charge times voltage, right? So the amount of potential energy, or the energy you can store in a capacitor, is going to be similar to that, charge times voltage. But it's the charge on the capacitor times the voltage on the capacitor. And it turns out those are divided by 2 in there, and that's because of calculus. The charging process is not exactly constant, and so you get it divided by 2 in there, and in the end you have Q times V divided by 2, and if you use the definition of capacitance to replace Q, you get C times V, and so you get C times V squared over 2. Or if you use the same definition to replace V with Q over C, then you get Q squared over 2C. But in either case, you get an equation to calculate the amount of charge. 1/2 CV squared, or 1/2 Q squared over C, or Q times V over 2. So if you know the charge and the voltage, you can calculate the energy. If you know the capacitance and the voltage, you can calculate the energy. If you know the charge and the capacitance, you can, any 2 of those 3 things, you can calculate the energy using these equations. So here's an automated external defibrillator. We have several of these at the college. And we have some practice ones too that don't actually dispel a charge. So, sorry, go ahead. We have them, they're downstairs in the EMT department. They're trainers. We used them for learning how to use the defibrillators in Cub Scouts and Boy Scouts. Anyway, so here we have a heart defibrillator. It's going to deliver 400 joules of energy, and it's going to discharge a capacitor that has 10,000 volts across it. So 10,000 volts, 400 joules. We know the amount of energy and we know the voltage, and they want us to calculate the capacitance of the capacitor. Okay, well, the energy of the capacitance is CV squared over 2, and we have been told the capacitance, no, we've been told the voltage and the energy. So we have voltage, energy, and we can calculate the capacitance from this equation. So we rearrange it, we get capacitance equals 2 times energy over voltage squared. Plug in our numbers, 2 times energy over voltage squared. We get 8 times 10 to the minus 6 farads. That doesn't seem like a very big capacitor. 8 microfarads? It is actually, especially because a capacitor has to be bigger to handle more voltage as well as more charge. So a capacitor that can hold 10,000 volts and 8 microcoulombs of energy, essentially, just a huge, or 8 microcoulombs of charge, is a huge capacitor if you're making it with normal materials. But if you're making it with newer materials like the aerogels, then you can make it small enough to carry around. So it is definitely a big capacitor.
At least back in the day, you knew if it was a large capacitor, you couldn't touch it. As long as one of the
Yeah.
transmitters could be tiny, it's still chances up.
Well, if it's tiny, it's not likely a high voltage. So like a 1 farad capacitor at 5 volts won't, the 5 volts is not enough voltage to penetrate your skin because your skin's dielectric constant is too high. But if it's a 200 volt capacitor at 1 farad, don't touch it. Okay, 200 volts is enough to go through your skin. That's enough to give you a really nice joule. But it will be a much bigger capacitor. It'll be significant. It will have signs on it saying "Do not touch." Excuse me. So that takes us to the end of the chapter and catches us up. We were a little bit behind, but not too much. Catches us up for this week. Let's take a look at the homework. I don't remember, since I just created the homework for this semester, I don't remember what I put in here. Okay, so here's a parallel plate capacitor. Question 1, another parallel plate capacitor. Van de Graaff generator. Metal spheres. Sparks, pulling protons, nucleus, field strength. So that's comparing voltage to field, which we learned about. Charges on the x-axis, potentials. So here we're talking about electric field and potential again. So that's another thing that we, electric field and potential again. So these are all things related to stuff like we did in the lab. Here's another one related to things like in the lab. Field and potential. So this one is how potential changes along the x-axis. And what is the electric field relative to the x-axis in each case. So in these cases, you have to remember that electric field is equal to potential divided by distance, right? So if if your potential is 5 at 0.01, if your voltage rather, if your potential is at 5 volts at a 0.1 distance, then you have to take 5 volts and divide by 0.1 to get the electric field, right? You have to have your voltage 9 divided by 0.3, right? What is the electric field relative to the x-axis in each case? How are they wanting you to answer that? Is the question. Okay, so if you take 5 divided by 0.1, you get 50, right? And if you take 7 divided by 0.2, that's like multiplying by 5. So that's 35, and this one was 50, right? Is that correct? 9 divided by 0.3 is like multiplying by 3-ish. So that's 20. That's not right. I'm not doing that right. What am I doing wrong? Electric field so relative to the x-axis is not what I'm calculating. Let me look at the code for this to see what they're actually asking us to do. What number was that? Electric field. What's that? 9? Yeah, so that's right. I think I figured it out already. So I go to here to edit. So essentially what you're doing is you're doing rise over run when you do that. Because the voltage, so it is just the slope of the line. Yeah. But why is it that I couldn't? Oh, I wasn't taking a difference. You have to take the difference in voltage between 2 points. And then the difference in the, so that's why. So you take the difference in voltage from 9 to 5, and then the difference in the x, and then that gives you, so it is just calculating the slope in that section. Yeah, so that's what it is. I was just looking at the x, the y over the x instead of difference in y over difference in x.
Difference in voltage over difference in distance.
That's correct. That's correct. Because the actual definition is a difference, right? It's an interesting way to do that problem. I've never seen that before. So in this, so what you do is you you could go from like 7 to 0 if you want. So going from 0 to 7, we have a change of negative as we go this way. So it's negative 7 over change of 0.7, right? So that one would be 490, right? No. Whatever it would be. It would be 7, it would be negative 7 divided by 0.7, which ends up being negative 10 or something like that, ish. And then this one would be a change from 3 up to 8 divided by a change of 1, right? So it would be 3 to 8, so it's 5. So that would be 8 minus 3 over 1 minus 0 in this case. This one would be 10 minus 4, which would be 6. So you take the end point, subtract the beginning point in the y direction. 10 minus 4 is 6. And then you take the end point, 0.6 minus 0, beginning point. So 6 over 0.6 in that one, and so on and so forth. So you're just calculating the slope to get the electric field in each one.
Yeah, it's
Yep, that's all it is. That is the correct way to do that. So in this case, they want you to calculate the electric field in this region of space, but what is the electric field going to be everywhere here if this is these are equipotential lines. So this shows equipotential lines. This would be 5 volts, 10 volts. You know that it's going to be going, the electric field is going to be going downward this way, because these are going downward. And they're going to be straight lines, parallel lines, because it's always perpendicular to the potential lines, right? So it's going to be a uniform field everywhere. Same field everywhere. Here's just calculating stuff with capacitance definitions. Same thing here. And same thing here. So the only thing I want to go back, sorry, did somebody have a question? No. The only thing I want to go back and review really quick is this right here, the electric potential due to a point charge. Just like with electric fields, remember when we talked about electric fields, you can have a point charge and you can create this equation for the electric field near to a point charge. You do the same thing for a potential. With electric field though, we also said if you have a sphere of a conductor, outside of that sphere, it's just like as if there was a point at the center of the sphere in your calculator. But inside the sphere, it's zero, right?
So the difference is from the center to
It has to be the center to the outside. And so there are a couple of problems in your homework where it talks about the Van de Graaff generator, which has a sphere right at the top of it, like that one there. And it behaves as if there is a point at the center. So you can calculate the voltage outside the sphere as if it was a point charge at the center of the sphere. But it only works on the outside of the sphere, again. Right? So right here they do that example.
I remember that posting me up because I couldn't tell if it was asking for some reason in my brain I couldn't figure out if it was asking from the center to the point outside the sphere for stuff greater than the radius of the sphere,
Yep.
or if it was asking for it from the edge of the sphere.
No, it's, you measure, you use your R distance always goes from center to center. Okay? So you can use this, but it only works for outside the sphere, outside the conducting sphere. So you treat it as if all the charge that's on the sphere is at the center of the sphere, and then you can calculate from there. You just have to be aware of that. I just wanted to go back and review that so you remember that, because I get a lot of questions about that every year. What's that? Yeah, section 19.3. Okay. So, I guess we're done. Done a little bit early, and that's fine. Does anybody have any questions from homework 19 that you want to talk about, or homework 18 if anybody's still finishing that one up?
Okay, so I saw there were two different equations that were I believe so it has voltage equals potential energy equals field. And there's also voltage equals the K constant.
Okay, so when they're talking about voltage equals potential energy over Q, that's a definition.
Yeah.
So voltage is what we call potential, and potential energy, they're related to each other, but they're not the same thing, and that's what they're trying to illustrate here. And the reason for that is because we want to be able to talk about the potential for something to have an energy somewhere without talking about how much charge that something might have. So we talk about potential energy per unit charge, and that is the definition of potential or voltage. But to calculate voltage, to actually calculate it for a particular charge that's creating a potential, you use K times the charge that's creating the potential divided by the distance from the potential to the point that you're interested in. Yeah, that's the relationship. One of them is a definition, one of them is a calculation. Which they should be, because they're kind of like, it's kind of like velocity and acceleration, right? One of them is the slope of the other, right? So that's what they are. So essentially, voltage essentially tells you how much electric field is changing in a region, as you're going in a particular direction. Just like acceleration tells you how much velocity is changing in a particular direction, right? So voltage is to electric field as acceleration is to velocity. No, let's see, is that right, or is it the other way around? It's actually the other way around. But anyway, they have that same kind of relationship.
because there's areas where there's stuff I should know how to do, it's simple. Like when we were reviewing right there about inverting, like adding up capacitors and the adding inverting.
Yeah.
Adding inverted fraction for 5 minutes there.
Flip it over. Don't feel bad. Algebra is easily the hardest mathematical subject on the planet. And, bar none. Everything else is simple compared to algebra if you have to do difficult algebra. Difficult algebra, I spent weeks doing difficult algebra problems in graduate school and never completed them because they were just too hard. And when I took them into a professor to get help, he cheated. He's like, well, we're just going to assume that stuff is just zero. Throw that out. And I'm like, well, I could have done it if I could have thrown that out. So it's not, don't feel bad. It happens to everybody. Any other question? You have any questions, Sam? It's your first day in our classroom.
Let's see. 8 on this week's homework.
Okay?
So, you're looking for the electric field vector. So where, like, at what point are you looking? What point are you trying to find the electric field?
Okay,
I
so
don't get that.
the electric field vector is going to have a direction that is always 90 degrees to equipotential lines. Now that's something that you may not have gathered from reading and other things because we learned that really well in the lab, and you haven't done the lab yet. But it is always perpendicular to the field. Okay? Excuse me. Always perpendicular to the equipotential lines. So here are your equipotential lines. So your electric field is going this way or this way, perpendicular to those lines. Excuse me. And also the electric field always points towards the increase in voltage. So the arrow is pointing towards the increase in voltage. And here it tells us that the lines increase by 500 volts for each line to the right. So in other words, if this one is 0, then this one is 500, and this one's 1,000. So it's increasing this way, so that tells us that our electric field is pointing upward and to the right. Right?
Well, see, I tried to do this problem earlier, but and mine goes the opposite way. It decreases by 1,000 every line to the
Okay,
right.
so yours would be going downward and to the left, right?
Yeah, but I was thinking, I don't know, I was like trying to figure out the answer for like the top right corner, basically. And so the above and to the right was correct.
Let me look at yours really quick.
I didn't do the right number twice like
So, at the origin, the potential is 9,000 volts, and they decrease each line to the right, so it's going down by 1,000 volts, down by 1,000 volts. So yours, and they say that it's 90 degrees above the horizontal. So like this. To the right. What does that mean?
that. I kind of
Yeah, it does mean that. It definitely is angled in that direction. Oh, no, that's correct, because you're, you have 9,000 volts here, and 8,000 So, no, that's correct, because it goes from high voltage to low voltage. Did I not, what did I say?
You said since yours was increasing, yours goes up and to the right.
So since mine is increasing,
The vector
okay,
goes up and to
so
the right.
I said it wrong.
So yours goes down to
Mine
the
goes down
left.
to the left, because it always goes, what I said wrong was, I think I said that it goes from low to high, but it doesn't, it goes from high to low. So the electric field goes from the high voltage. So essentially what you can think is that high voltage is where your positive charges would be. So since your high voltage is down here and your lower voltage is up here, somewhere down here you have some positive charges that are causing this field. Somewhere up here you have negative charges. So that's what that means. And so yours definitely does go upward to that.
Okay, so when you're trying to find the electric field, so what points are you supposed to use?
Okay, so to calculate the actual electric field when you have this is really simple. You just calculate the slope of those lines.
Which is the rise or the
Yep. Yep. So you just pick one of these lines and calculate. So since they're all parallel, the electric field is the same everywhere, right? If these were lines that weren't parallel, they were squiggly all over the place, or all kinds of funky angles, then you'd have a hard time because the electric field would be changing everywhere. But in this one, they're all the same. They're all parallel, so they're all the same slope, so the electric field is the same everywhere. So just pick a line and calculate the slope.
Well, so then they're all matching at the same point, so would there just be one?
Yeah, your slope here is actually negative.
Yeah.
So it's a negative. And I don't know if they care for the sign. Let me look and see if they care about the sign.
So that would be the distance. The pole doesn't change.
I don't, let's see. I don't think they care about, I think they just want that magnitude because they're asking the direction differently anyway.
Okay, so
But
then,
let me just check really quick.
but since the electric field is the volts divided by distance, since the distance is always going to be -1.
Okay, so, hold on a second. Let me see what we're actually doing here. Oh, sorry, no. In this one, it's not the slope because I forgot that this is a graph in X and Y, not voltage. That's why I was confused earlier too. Because the next problem is the graph is voltage per distance. This one is just X and Y. So that's the problem. Sorry, that's my fault. So in this case, we have a potential that's changing 9,000 volts.
Right.
So it goes from 9,000 volts to 8,000 volts. So that's the thing that you need to, so from here to here you have 9 to 8,000, right?
Yes.
So that's the thing that you have to use as your Y in your slope or something. So you take the voltage change divided by the distance. So the voltage change from here to here is 9,000 to 8,000, so that's 1,000 volts. And then you divide that by the distance from here to here, which is not 1, it's actually, you have to use a Pythagorean theorem, right? Because you're going from 1 to 2, actually going from 0 to 2, and then 0 to 2 Pythagorean theorem. So it's 2 times 2 squared to the square root, essentially. So it's 4, not 4. Square root of 2 times 2. But anyway, let me show you that on the board really quick.
So then it would be 2.
So, no, not quite. It would be square root of 2 times 2. But this is what it looks like. You have voltage, electric field equals voltage divided by distance. Change in voltage divided by change in distance. So that's the definition. In problem 9, it's easy because voltage is on the y-axis and distance is on the x-axis, so you just calculate the slope. But in problem 8, it's not that. On this graph, you have distance is represented by both sides of your graph, and your voltage is represented by the red lines. So we have to take our change in voltage is going from, so if we go from the origin down to the first line, that's 9,000 minus 8,000. That's our change in voltage, right?
Right.
And our change in distance is this distance across this little cube that has a side 2 and a side 2, which is 2 squared plus 2 squared, square root, right? Right?
Yes.
Okay. So that's our thing, that's our distance down here, 2 squared plus 2 squared, right? Which happens to be 4 plus 4, which is square root of 8. So it's 9,000, so up here we have 1,000 volts, which is the difference. And then down here, it's the square root of 8, which is 2 square root 2. So if you take 1,000 and divide it by the square root of 8, you should get the proper answer. Do you have any more questions?
Oh, lots.
Oh, okay.
So that one would be about 353.
That's correct. 353.6.
So would that be the same for even if you picked like the
Yeah.
6 to 6 point?
Because these are all parallel lines that are equally spaced across here.
So it's all gonna
It'll
come
all be
out
the
to
same.
about
Yep, it all come out exactly the same.
Okay.
If these lines were closer together, or if they were, not parallel, then it would be a different story.
Okay, so then this, like the second part of that question, where it says I put 90 degrees above the horizontal to the right.
So, but
going
it's
back
actually,
to the right.
it's going this way. So that's 90, it's not 90 degrees, that's 45.
Oh, I was just doing the end point
Yeah.
where it started. Okay.
Yep, so just right here.
Question 9. We kind of went over that one in class, but I tried it and it didn't work.
I accidentally showed your grades on your 2 homework assignments. I said I accidentally showed your grades on this video. Do you want me to erase those from the video?
No, it doesn't matter.
Doesn't matter to you? Okay.
I'm not done with it. I did my first attempts. Now we're going back to the second attempt.
Sometimes I forget that the grades show up with names if I switch back and forth between screens. Forget that I'm recording. But if it doesn't bother you, it's not a big deal.
No, some people do this too. I'll probably go back and look at it. Okay, so number 9.
Number
We're supposed
9.
to do the
Same
change.
same assignment?
Yeah.
Yeah. So number 9, since it's the voltage that's on the y-axis and the distance that's on the x-axis, then voltage divided by distance, just like in this equation, is just the slope of these lines. So you just calculate the slope of each and you're good to go.
Well, so like my first one, it starts at 7 and ends at like 0.45.
On which axis?
It's going down to the right, so it starts at 7 volts.
Okay.
You have one similar. You can probably find it. Yeah, that guy. It's
This
similar, so it looks like that.
Okay.
So mine starts at 7 and it ends at 0.45.
Okay.
So I did.
I would just pick 2 points where it crosses a definite little point there, where it crosses a hash mark between x and y. Just pick 2 points like that and use those as your beginning and ending point. Since they're all straight lines, it doesn't matter where you start and end.
Okay, so I can use 4 and 1.
Yeah. Use 4 and 1 and then do the other one and divide the difference in y by the difference in x. And make sure that you,
I thought we were just supposed to divide like y divided by x.
no, the difference in y divided by the difference in x.
Okay, so since I'm going from 7 to 0, it would be -7.
Yep.
And then I'm going from 0 to 0.45, so it would be 0.45.
Yep.
So I did -7 divided by 0.45.
Yes.
That was wrong.
Okay, so that may be a problem because, let's see what they're saying here.
That was my -15.55.
So that one, since you're doing about 0.45, it may have had a problem with that. It may have had a problem with you.
Yeah, it might be a little bit further than.
Yeah. So pick 2 points that are definitely going through points that can be
Okay, so I can.
better
use
estimated.
-4 divided by. Is that gonna be okay though? Because it's gonna be the same, it's gonna be different on any point I would make then.
It won't be because it's a straight line. The slope should be the same. And I don't know if they want you to include the negative in there. That's one thing I should check there for you.
Yeah, you can open it, it's fine.
What's that?
You can open mine, I don't care. Because then it would be, I could go from 4 to 0.4, so it'd be -10.
It's 9.
That first one.
Yeah, they don't. So what they're saying is that, so you went from where? You went from
I went
4?
from 7 to retry, I went from 4 to 0.4.
So you went from 4 down to where?
The 0.4.
So 4 to 1?
Oh, yeah.
So that would
I
be
guess that'd 3.
That would be 3 over, and the 4 goes from, 4 starts you at 0.2 to 0.4. So you'd have 3
Divided by 0.2.
divided by 0.2.
-25.
Let's see. Is that right? You're going from. So you're going from 4 down to 1, so that's 3, divided by 0.2 to 0.4, which is,
Oh, that was 15.
yeah, that one is 15. So 3 divided by 0.2 is 15.
Well, that makes
So
sense.
they- and
Because
they
my
don't-
original answer was -15.55.
Yeah, so you were close, but they don't want negatives either. So
So don't even take that.
yeah, they just want to know the absolute value.
Okay. So.
Well, they're showing an answer of -10 for the next one, so that's not true. They do want negatives, but why?
Which. On the one where it starts at 4 and goes up to 10.
Yeah, let me look at the definition really quick because we may be getting the definition incorrect.
Because I had the answer on that one as 10, and it was wrong.
Yeah, it should be -10.
So
But I
was
think
gonna
that
write it.
they are including the negatives. But if we go back here to electric potential, the definition,
Mhm.
I believe there is actually a negative sign on it, and that's because of That's because of our friend Benjamin Franklin, because he chose electrons to be negatives. But let's take a look. Yeah, right here. The definition does have a negative on it.
What's the S?
They use S instead of X or D or R.
Like
Just
distance?
it's just distance. Yeah, it confuses the heck
So
out of
it's
people. But
equals negative.
so it is a negative
The change
delta
in
V over.
voltage
Yeah,
or the change in distance.
yeah. There is a
There
negative.
we go.
So on number 9, it's the negative of the slope.
So whatever my answer would be, it just has to be the opposite.
And since this is the first time I'm using this system for this class, you guys get to kind of be guinea pigs.
Yeah.
So as I go through and see these questions, I like that question, but I would like to be more clear. I'd like to tell the students, sign does matter, so you need to make sure that you have the definition
Right.
correct.
And I had
This-
on the first assignment, I had so many problems putting answers in because it wouldn't take times 10 to the whatever.
Yeah.
Like it'll let you write that out on some
Right.
questions and it takes it, and some it wouldn't. So you had to type point 10 zeros 2
Yeah.
5, and I would
And
take that.
and that's a code. Those are coding issues inside the computer
Right.
computer program. And so those are things that I just need to fix as time goes on.
Okay, so the last one
because I didn't write any of these questions. I just used them.
Oh, yeah.
But I have changed several of them as we've noticed different quirkinesses about the different problems. I've tried to improve them, and I'm not a great programmer, but I can.
I wouldn't
Do
have
enough.
any clue. So my last one is like. So I was really close on all these.
I do have a class that comes in at 11, but it's a lab for my physical science class.
Okay.
So if you want to stay and do homework or work on labs or whatever else you can, there will be room here. Don't have a lot of students in that class, so it shouldn't be a problem.
Physical science, you said?
Yeah, which is like covers chemistry and physics and geology and atmospheric science. And just a very, it's like basic biology. It covers a lot of things.
Yes. Okay, and then number 10, it's asking for the length of the parallel plates, and I have the thickness and the dielectric constant, so I was going to use that equation.
So that's where you use this equation.
C equals the dielectric constant over area over distance or whatever.
Yeah, but in place of area, you replace that with the calculation for area, which is length times length, right?
Right,
Yeah.
because it says it's a square, so it's not, so it'll all be the same.
So you
But my
calculate.
big one is the distance. What is my,
So the thickness of your dielectric will be the distance between your plates.
okay. Okay, and then it was, what is U? What does a U stand for?
Where are we at?
Number 10. I was looking for the equation for that one. Well, I know it's for energy.
Oh yeah. So U is potential energy. That's just another. They often use U for PE. So potential energy is
Okay.
the same as U.
But I got the Q part of that.
Yep.
So C.
That's like the U is the stored energy in the capacitor.
So C would be the 850 pico, whatever.
Yeah,
that-
farads.
Farads.
That's correct.
Okay. To determine length, am I going to have to change picofarads to just farads?
Yeah, you
I already
definitely
have,
want.
I guess.
Yeah, because pico is 10 to the minus 12.
Right.
So have you ever been over to the nuclear medicine wing of the hospital?
Oh yeah, they're right across the hall.
Oh, all right. Sometimes we go on a tour of that place towards the end of class because it's all related
For
to this
this
stuff.
class gonna come in.
Go look at the positron emission tomography.
Oh, you go to the PET scanner?
We've seen
Like
both
big
of them.
CT machine guy?
We've been to the CT, we've been to the
That is-
MRI room.
yeah.
We've gone to all those places because they're all related to the science we study in this semester. So,
Well, the MRI is cool.
what's really cool about the MRI is that it has a huge current going through that big thing. That current is not driven by anything. Did you know that?
Uh-uh.
When they installed it, they brought in a huge electrical generator to start that current, to get it going,
Mhm.
and then they disconnected it and it's been running ever since because it's a superconductor. So it has no resistance.
Yeah.
That's why it's so noisy in there, because of all the liquid helium that has to be pumped into there to keep it cold.
Yeah, there's a lot. It does get really loud. That room outside though, they made it soundproof or whatever. Oh, you don't hear a thing.
Yep,
It's nice.
it is. I'll be right back.
Okay.
Remember, there's a score for us. What we'll do is split you guys up into 2 groups, and we'll get you set up here in this lab. It's pretty much self-guided. So in the beginning, I'm going to give you some little introduction to the equipment. And actually, you guys can use the same lab sheets together for both of them. Pull it out together. You two can do it the same. In this lab, you'll be you'll be using a motion detector. put in the way. But, so you'll each be using a motion detector. These are kind of like electronic bats. You have an ultrasound emitter in them. And you'll hear some clicking, which is not actually the ultrasound. The clicking is just the electronics inside it. But it has an ultrasound emitter and an ultrasound detector in it. And it shoots sound outward. And that sound bounces off of things that are either moving or sitting still. It comes back and detects the sounds that come back. And through that detection and some software, it can actually tell if things are sitting still, if they're moving, how fast they're moving, how far away they are. It does have a detection distance, minimum detection distance of about a third of a meter, so if you're much closer than that, it doesn't detect very well. It doesn't give you good measurements. And it has a maximum detection distance of about 2 to 3 meters, so if you're much further away than that, it won't detect very well. You want to make sure that while you're using it with a moving person, that you have it switched to the moving person here, because that gives it a little bit wider beam, so that it can detect out a little further. We both already said that. You also will need to connect them to the computer up here, and you need to plug in the computer and turn them on. But they plug in through a logging device, which is this. Going up. This is the device here, this blue device. This will be like hundreds of cords tuned up with it. Like the last semester was some kind of wars on the But this device, which should be connected to the computer and to power supply. So there's one cable out going to the power block on the table, one cord that will go to the back of the computer. This. And computer log. Plug in the computer. Put that in back of the computer. All right. Okay, so this goes in, this plugs into the side that says Dig Sonic. So it's this side right here, because it is a digital sonic signal. And then you're going to put this on the edge of your table. Now you don't really want to be pointing them towards each other. So one of you is going to have to walk one way, like maybe this way, and one of your teams is going to have to walk this way. pointing towards each other, they can refer to each other. I don't care which you choose to do, but whatever you choose to do, you're going to have to set up some tape on the floor. Now, you can see lots of people have done this, and I clean them off every year, but then we put new tape down every year. You're going to need a meter stick, which I have set up. There's one for you. And one for you guys. There's some tape that we can share. Be friendly and share the tape. But the idea is to use this motion detector to study velocity, position, displacement, acceleration, all these kinds of things that we've been learning this first week. And you're going to learn how to associate these things with graphs and how to calculate these things with the equations we've learned, how to do some analysis. And like I said, it's kind of self-guided. You have these instructions to do, and within the instructions, there are going to be questions you have to answer. And you have to write some things down. You have to draw some things. At the beginning, you can see here, the very first thing they say, if you're starting at the half meter, you make a distance time graph walking away from it, right? So they're telling you what you're going to do. You're going to start at a certain place, you're going to walk away from the thing, and then you're going to make a graph on the computer and transfer it onto your paper. So, open is your computer on? There's a button right behind it on the left side there. A little round button on the left corner. So what you're going to do is go down to the bottom, the toolbar across the bottom there, and you're looking for this icon here. It has a little calculator. This is a program called Vernier Logger Pro. Of all the different programs you can use to graph things using scientific instruments, I like this one. It's very intuitive. It's kind of just does its thing. You don't have to hardly work at it. If you open it up, it will detect the devices that you have connected, and it will set up an appropriate graph. And then setting up other graphs is not very difficult. So, but if you do have any troubles with it, if you're not understanding something, come and get me. If you're not understanding something with the lab, come and get me. I will either be in and around the lab doing some things, or I might even be in my office from time to time. But I'm going to pretty much turn you loose to do this stuff as much as you can on your own with your partner, so that you can learn. I asked for the wired keyboards because I didn't want to change batteries all the time. And of course, nobody listened and nobody read anything that I wrote down when I ordered these computers. And they ordered these ones, which I didn't want to deal with at all. Do you have a mouse? Go to see. just go ahead and click somewhere. This mouse that you're using is a 2-button mouse, even though it looks like it has no buttons. So if you click on the left side of it, it behaves like the first click. If you click on the right side, it's like the left click. So just be aware of that. And it's lost your mouse. Like I said, but see, it's opened it up and it's what it's showing you. Turn it on. Okay, so there should be a blinking light. You have a blinking light on your little rocker. Your logger is blinking light. You've got graphs. So yours is showing right now velocity and position. One shows position, one shows velocity. And if you look at the top of the screen, you've got this little play button up there, that green button. If you push that play button, it will start your collection. So go ahead and push that. Let's try it out. The green button says collect. Push that. Hear that? So it's collecting. How long does it collect for? It looks like it's set to collect for 5 seconds. Did yours collect for 5 seconds?
Not for.
Looks like about 5 seconds. Now, if you move it around, or if you move something around in front of it, you'll see go ahead and press collect again. So if I move my hand around in front of it while it's collecting, you can see that it will. I was too close to it. You lower it a little bit from my hand. See that we move a little bit there. But it's only collecting for 5 seconds, and maybe you want more time. If you want more time, you want to go up to the button that says experiment. At the very top, there's a file. And we'll go to experiment. Where it says experiment. And you go down to, you can either extend the collection right there, you go to extend collection, or you can go to data collection. So go to data. Go to data collection. When you open up data collection, it opens up this window that gives you the options to change how many seconds you're going to collect and how often you collect. So if you want to collect for 10 seconds, you go to duration, you can go to 10 or 15 or whatever you want. If you want to change how often it collects, you go down to samples per second, which is sampling rate. And you can change that right now, it's at 20, which is pretty good. But you can change both of those things. And you can do lots of things. You can even actually collect data continuously, which is, where is it? So there's a button that says continuous data collection. So we'll just continuously collect data until we tell it to stop. So those options are available to you as you go through the experiment. And you will be asked to change those things, so be aware of that. So go ahead and close out of that. And let's go to the graphs. You'll notice that there are 3 graphs and a little data box on your window. You have the two graphical graphs, the time and position and the time and velocity graph. But you also have the chart over to the left, which shows you the actual data points. It actually shows you the numbers that your motion detector is feeding to the computer. So one of the numbers is a time, the other number is a position, the other number is a velocity for each time stamp. So if you want to look up something specific, you can see it right on that chart. If you want to see what position it's reading right now, you look down in that bottom left corner. So if you press collect again, press collect, and then look in that bottom left corner, it shows you the position all the time. It shows you a number for the position at different times. Let's see. If you need to read something outside the range of the graph, if your graph goes off the chart, for example, usually Vernier will automatically adjust so that you can see it. But if it doesn't and you want to see off the chart, you click on the biggest number on the y-axis, so go up to the biggest number on the y-axis. Click on it, And you can change that. So if you change it upward, you can zoom out. If you change it downward, you can zoom in. Or you can use the tools at the top. There's zoom tools at the top for zooming in and zooming out of your chart, so you can use those. What else do I want to tell you? Oh, another way to get to your data collection box is to click this button right here for data collection. Click on that. It'll open up that box, so there's another quick little button. And I think that's about all you need to know to get started on this. As you read through here, they're going to tell you specific activities to do and specific ways to do them, so set them up carefully. If you guys want to go this way, or maybe we'll point you guys this way, and you can kind of look off in that direction, walk through, walking that way. Make sure that you make your measurements from the front of the detector, not from the table. So if you're measuring 1 meter from your detector, measure from the front of the detector, 1 meter. And then another meter. And put your tape on the floor accordingly. Besides that, I'm going to turn you loose and let you play around with this. We have about 2 hours to do this, an hour and 45 minutes. You guys, yeah, you can share the tape. I also have another one somewhere. These things all over the place, actually. Depends on the review. I'm not the most organized person, well discovered. But I do try. Okay, did you have any other questions? I have to stop this recording before I forget.